Welcome to this explainer. Okay, if you've ever stared at a math problem full of letters and thought, literally, when am I ever going to use this in real life? Well, you are in exactly the right place. Today, we're demystifying algebraic formulas. We're going to take them completely out of the dusty textbook and drop them right into the real world, from figuring out bakery discounts to managing your lunch money at the school canteen. My goal here is to show you that algebra isn't just a bunch of random symbols. It's actually a super powerful tool you can use to decode everyday life.
Okay, let's dive right into this roadmap. We're going to cover the anatomy of a formula, forming formulas, changing the subject, determining variable values, solving real-world problems, and wrap it all up with a quick summary and revision.
Section 1. Anatomy of a formula.
So how do we mathematically calculate the exact price of a chocolate cake? Or honestly, any item for that matter? I want to hook you on this idea right from the start. Algebra is not just a random alphabet soup. Those letters are actually a highly efficient way to figure out real, tangible things, like the total cost of your favorite dessert when you're buying a bunch of them for a party. And to do that, we need a formula.
What's really fascinating here is the crucial distinction between a formula and a standard equation. A formula absolutely must have more than one variable. If it only has one, well, it's just a standard equation. Take the classic area formula, for instance. A equals pi r squared. You've got A for area and R for radius, two variables connecting to describe something real.
Section 2. Forming formulas. Remember, these letters are just placeholders for real things. Imagine you're organizing a massive cultural performance, right? You've got different groups of dancers. We can just let A represent the number of Chinese dancers, B for Kuda Kit Pang dancers, and C for the Indian and Malay dancers. Now, if we want to know the total number of all the dancers, let's call that W. We just add them up based on how many are in each specific routine. So our total W equals 3A plus 7B plus 3C. Boom! We just built a formula that perfectly describes our entire dance troupe.
Let's apply this to something a little sweeter. Picture a bakery run by, let's say, Susie. Susie sells chocolate cake for 3 ringgit a slice. Let's call the number of chocolate cake slices M. Now, she also sells cheesecake, but it's exactly twice the price of the chocolate cake. So the cheesecake, which we'll call N, is 6 ringgit a slice.
And this brilliantly illustrates how we can form a pretty complex formula from a completely real scenario. Let's say Susie is having a grand opening and giving a 10% discount on all cakes. We need a formula for the final selling price. Let's call it Z. Step 1, we just multiply the items by their price, 3M plus 6N. Step 2, we apply that 10% discount. Now, if you're taking 10% off, you are actually paying 90% of the original price, right? So we multiply the whole shebang by 90%, or 0.9. Step 3, distribute that 0.9 into the brackets. 0.9 times 3 is 2.7, and 0.9 times 6 is 5.4. So our final, beautiful formula for the total price Z is 2.7M plus 5.4N. You can now plug in any number of cakes into M and N and instantly know your discounted price. How cool is that?
Section 3. Changing the subject. Now, when we talk about the subject of a formula, we mean the variable that is all by itself, totally isolated, representing the final answer we're actually looking for. And there are 3 absolute, non-negotiable golden rules here. First, the subject is a dependent variable, meaning it depends on whatever the other letters are up to. Second, the subject must be written cleanly on the left side of the equation, always the left. And third, the coefficient, that's the number chilling right next to the letter, it must be exactly 1. No exceptions. You can't have 2x as the subject, it has to be just x. Let's look at a simple balancing act. Say our original equation is Q equals M plus P. But what if we actually want M to be the subject? We need to isolate M. To do that, we move P to the other side using inverse operations. Since P is currently being added, we just do the opposite. We subtract it from both sides. Let's flip the equation so M is on the left, which gives us M plus P equals Q, and then subtract P. Now our new formula is M equals Q minus P. See? We've successfully changed the subject. But you know what happens when we run into trickier things like squares and square roots? Well, that golden rule of inverse operations absolutely still applies. If s equals p squared and we want p as the subject, we have to get rid of that square. The total opposite of squaring is square rooting, so we just square root both sides, giving us p equals the square root of s. Conversely, if q equals the square root of p, we do the exact opposite. We square both sides to free that p. That leaves us with p equals q squared. Honestly, as long as you do the exact same inverse operation to both sides, your equation stays perfectly balanced.
Section 4. Determining variable values.
Okay, let's walk through this step by step. Let's say our formula is W equals 7t minus 5u, and we are given the actual values, t equals 3 and u equals -2. In step 3, we literally just substitute those numbers right where the letters are. This gives us W equals 7 times 3 minus 5 times -2. Now, pay super close attention to the negative numbers here because this is where a lot of people slip up. 7 times 3 is 21, but minus 5 times -2, that becomes a positive 10. So our final calculation is W equals 21 plus 10, meaning W is exactly 31.
Now let's see how this builds when we work backwards. We have that same formula, W equals 7t minus 5u. But this time around, we already know the total. We are given W equals 15 and U equals 4. We need to find T. Step 2, we substitute what we know. 15 equals 7t minus 5 times 4. Let's simplify that in step 3. 15 equals 7t minus 20. And now we just bust out our inverse operations from earlier. We add 20 to both sides to get 35 equals 7t. Finally, divide by 7 and we discover that t equals 5. Look at that. You just cracked the code backwards.
Section 5. Solving real-world problems.
All right, let's set the stage for the boss battle. Asman goes to the canteen with 5 ringgit. He buys 2 buns and 1 piece of fried chicken. Now we are told the fried chicken costs exactly twice as much as a bun. After he buys this delicious lunch, he saves 1 ringgit. I want you to think about how we can take this story, this totally everyday lunch purchase, and turn it into a mathematical formula to find out exactly how much the food costs. Here's exactly how we translate that story into variables. Step 1. If Asman started with 5 ringgit and saved 1 ringgit, he spent exactly 4 ringgit. We know our total. Step 2. Let's assign our variables. We don't know the price of a single bun, so let's call it x. Since the chicken is twice the price, the chicken is 2x. He bought 2 buns, so that's 2 times x, plus 1 piece of chicken, which is 1 times 2x. So our equation is 2x plus 2x equals 4. Step 3, we combine our terms. 4x equals 4, which obviously means x equals 1. And just like that, step 4 gives us our answer. Since x is the bun, a bun costs 1 ringgit. Since the chicken is 2x, the chicken costs 2 ringgit.
Now for the absolute triumph. The problem asks, if Osman comes to school the next day with 12 ringgit and he buys the exact same number of buns, which is 2 buns, how many pieces of fried chicken can he buy? Well, 2 buns cost 2 ringgit total. If he pays with his 12 ringgit, he has 10 ringgit left over. Since we know fried chicken costs 2 ringgit each, we simply divide that remaining 10 by 2. He can buy exactly 5 pieces of fried chicken. We literally just used algebra to perfectly budget his lunch.
Section 6, Summary and Revision. So, the really crucial point to take away here is that formulas are not just random letters. They are powerful connections between multiple variables that represent real tangible things. Second, when you are changing the subject of a formula, you've got to isolate it on the left side, and it must have a coefficient of 1. Third, to manipulate these formulas, we use inverse operations to smoothly move terms, squares, and roots back and forth across the equal sign. And finally, when we substitute known values into these formulas, being very, very careful with our positive and negative numbers, we can solve real-world puzzles, just like we did at the canteen. I want to leave you with this thought. If algebra can perfectly calculate your exact change at the canteen or figure out the precise discount on Susie's cakes, what personal budget or daily puzzle could you solve by forming your own formula today? You now have the exact toolkit to do it. Thank you so much for joining me on this explainer. Keep practicing, keep calculating, and I'll catch you next time.